So today we will be doing another example of competitive learning network, and this time we would be doing a supervised learning algorithm. So this example today we are doing is learning vector quantization. So this is another pattern clustering or pattern matching algorithm, which is again based on the same concept that we were doing for the max net neural network, that we were doing for the Conan network. That is the winner takes all strategy. But unlike Conan and Soam, this LVQ would follow a supervised learning strategy, right? Because if you remember, Conan was following a unsupervised learning algorithm. Now, the architecture of LVQ would be almost similar to that of Soam, that is self-organizing map. I'm talking about Conan's Soam, right? Only with the exception that this time we are not going to use the topological neighborhood concept. If you remember in Soam that we used to update the weights corresponding to all the winning neurons. Whatever neuron was declared winner, we used to look into its neighborhood defined by the topological neighborhood structure. And then we used to update those weights. Over here, this concept would be missing. Now, this is also important. There would be as many as input units as the number of components in the input vector. That is, for example, I have an input vector of the size, suppose x1, x2, x3, and x4. There are 4 components in this case. So the number of inputs in it would be same as the number of components. That is, over here, the size was 4, so number of inputs would be 4, right? Now, each output unit would represent a cluster, would have a known cluster. And that is why we are calling it as what? A supervised learning algorithm. Although we should not have called clustering, but since these clusters are known, these have a designated labels. So we would be calling them as each and every training pair would have a designated cluster, right? And therefore, this is a clustering algorithm. Now, the training set will consist of the number of training vectors, and each of which would be designated with a known cluster. So this would be a setup. So we have a training vectors, and we have a known clustered output units defined for each and every input units, right? Now, during each epoch, I hope everyone knows about epoch. Epoch is what? Epoch consists of all the training vectors, right? So once I've trained all the training vectors, that completes one epoch, right? So during each epoch, the weights are adjusted to accommodate the training vectors on the basis of known clusters, because the clusters are already designated. So overall objective of this LVQ is to find the output unit that is closest to the input vector. If you remember, this was the same objective we used to define for Conan network also, right? So the objective remains same. The only thing is the treatment, the algorithm, the learning algorithm changes, the learning type changes. Now, in order to ensure that this algorithm finds the code vector, I hope everyone knows code vector is the exemplar code, right? We'll be talking about in more details. So in order to ensure that this algorithm finds a code vector W closest to the input vector, we have to define some means, we have to define some criteria, right? That is, again, the concept remains same, that we need to look for the closeness between your input vector and the weight vector, right? So suppose if I have input pattern, say suppose S, and the code vector or the weight matrix W, right? Then if S and W map to the same cluster, that is for a given input and the weight matrix, if that input maps to the same cluster, then this code vector W is moved closer to S, right? How that closeness definition would be defined, we'll see through an example. Or otherwise, this W is moved away from X. This W is the code vector or the exemplar code. So the code vector would be either moved towards the input pattern of which we are considering, or either it would be moved away from that input pattern. Because ultimately we need to, for each and every input, we need to find the designated cluster, right? that is how the training would continue. So let us do the algorithm along with the working example. So this example would also cover the algorithm part, right? So an example, we are taking these 5 input patterns, and their corresponding cluster inputs are given, right? So if you know, can see that each of these input units have what, 4 components, right? Now, based on this, a simple structure could look like this. So we have 4 inputs, and we have 2 designated clusters. For each and every input, there is a known cluster, either C1 or C2. And since this is a supervised learning algorithm, so we have to talk about that how training can take place, and then we will also see that how testing can be done. Now, what we have done is we have to decide among these 5 input patterns that what all patterns I would take for training, and also what all patterns or what all inputs I would use for my exemplar code, because I have to define the code vector also, and then I have to designate among these 5 that what all would be my training vector. So what we have done is, again, this is just a random thought, that among these 5 patterns, I have taken S2, S3, and S5 as my training vectors along with their clusters. And other vector, that is S1 and S4, I have used for defining my code vector. So this was, these 2 code vectors was corresponding to S1 and S4. So this is code vector 1, column 1 is code vector 1, which is actually corresponding to my uh, input pattern 1, right? If we say 1,000, so 1,000, right? And similarly, you have taken the this as a code vector, that is pattern 4, to be the code vector 2, that is 0,001. So among these 5 patterns, I have taken 2 to be the code vector. And why have we taken only 2 code vectors? Because I had only 2 clusters. So one of the code vectors, that is first column, would designate towards cluster C1, suppose, and the second would designate towards C2. So I have, among these 5 patterns, I have to choose one such pattern which corresponds to C1 and other which corresponds to C2, right? I could not have taken pattern 1 and 2 because both are corresponding to same cluster. I hope that is clear. And which all you have to take as a code vector, that is something you can decide upon on a random basis or arbitrary basis. So as of now, the setup is ready for the algorithm to run. So we have 3 training patterns and we have 2 exemplar codes, right? So there are 4 components in training vectors and 2 clusters. So as we have already spoken in the initial part, since the number of components in each training pair is 4, and each input pattern is 4, so therefore the target network will have 4 inputs and 2 clusters as the final output, right? Now this is the training vectors. Exemplars we have set 1 and 4, and rest of the vectors 2, 3, 5 have been used for training, right? So as a part of the first step of the algorithm, as we all know in neural networks, we have to do the initialization part. Now in order to initialize the weight vector, we have initialized the weight vector as the code vectors. And for initialization, we are taking the learning rate to be 0.2. Again, this is something which we have taken arbitrarily. Obviously, this value should be lower value in the first step, or it can be any value between 0 and 1. That would be more preferable. But we have just taken 0.2 as my learning rate. And we have already initialized S1, S4, as I've said. One thing more, that as we have learned in the previous network of Cohen also, that this learning rate would decrease by some factor for each and every epoch till the convergence takes place, right? So over here, what we have decided, that this would be geometrically decreased by the iteration, by each iteration, that is after each epoch, by a factor of 0.5. That is a standard way to do so, right? Now, the first step of the algorithm is we have to decide the stopping condition criteria, right? So the stopping condition criteria over here is that we stop when the process converges. So convergence takes place when there is no perceptible change, or when the change from one epoch to the next epoch in terms of the code vector. That is, when the code vectors would stop changing their values. That is a stage when I would decide that this would end, or this would be the stopping condition, or this would be the convergence stage. So initially, definitely, the stopping condition is false. So let us start the algorithm. So this is the setup, right? So step 2. Now for each input training pair, we have 3 input training pairs. I hope you remember, that is S2, S3, and S5. These were training pairs, and exemplar codes were S1 and S4. So for each of the training vectors, suppose we start with S2. S2 is what? This one. S2 is 0, 1, 1, 0, 1, 0, 0, and it is mapped to cluster C1. So we are taking this input vector, right? So we have taken the first pattern, all right? Now what we have to do as a step 3, that we have to find the distance dj of this input vector from each of the code vector, or from each of the exemplar code. And we have 2 exemplar codes, right? Corresponding to D1 and D2. So the distance of this input pattern S2 from the code vectors D1 and D2 that we are calculating. And this distance, what we have done is we have just taken the equivalent distance, although there could be some other distance metrics could have been used, but equivalent being one of the most popular distance metrics, that is what we are using it. So what we have done is we have taken what? The subtraction of this xi corresponding to the code vector value, right? So wij was what? If you remember, wij is 100 for first code vector and 0001 for the second code vector. So just remember this value 1000 and 0001, right? So what we are going to do is, so corresponding to D1, that is the first code vector, which was of the value 1000, right? So each of the input vector, that is input vectors x1, x2, x3, x4. So what we have done is x1, that is 0. Similarly, x2, that is 1. Then x3, 0. And x4, again 0. It has been subtracted from the first code vector. The first code vector was what? 1000. So 1, 0, 0, and 0, right? So this is how we would obtain a value of 2. And similar case, we would be doing the same process corresponding to S2 with respect to the code vector 2. So over there, the value was what? 0, 0, 0, 1, isn't it? The second code vector was 0, 0, 0, and 1. So after obtaining these 2 values, what we found is both the values are giving us 2, right? So as a step 4, we'll move to step 4, which says that find the index j for which of these dj's is minimum, right? Whether d1 is minimum or d2 is minimum. Over here, what we find that both the values are same, right? So arbitrarily, we have to make or decide that which one would be declared as a winner. So suppose arbitrarily we have decided that we would declare j is equal to be the winner. That is, code vector 2 is declared winner at this point of time, corresponding to the input pattern S2, right? Now what we have to do is we have to decide like on what basis that we have already discussed that how these weights would be updated, right? That is, updated means how this code vector would be updated, right? So there were 2 conditions. If this target must means what? The designated cluster for each and every input vector. If the designated cluster is equal to the winner neuron, the neuron which has been declared winner. For example, over here we declared j is equal to 2. Second code vector was declared winner. So if t is equal to cj, that is the cluster which is the target cluster corresponding to the input vector. For example, in our case, we were training the second input pattern, right? And for the second input pattern, the winner was, if you remember, for second input pattern, winner was C1. So here the S2 was designated T as C1, right? So if this is the case, if both the values become equal, then this is the first condition, and this condition says that we have to move the code vector, the winner code vector, or whatever code vector we have declared as a winner, that has to be moved closer to the input pattern, right? And how we would move closer to the input pattern? By using this scheme, where the old weight is added with your learning rate into difference of your input value and the corresponding code vector, right? And the else case is what? If the values are not equal, as the case we have obtained, right? In that case, the concept is to move that code vector away from S, right? And the only difference in these two formulas is that these two signs are different, right? So in our example, since T, that is T was for corresponding to S2 vector, the designated cluster was C1, isn't it? But we have declared C2 as the winner. So in this case, for example, the condition, if condition is not going to satisfy, we have to move to the else condition, isn't it? Because both the values are not same. So hence the code vector should be moved away from the training pattern, right? So corresponding to S2, what we have done is we have taken this formula. So what we would be doing is we would be updating each and every value of the code vector 2, right? The code vector 2, if you remember, was, I suppose, value 0001. Yes, is that? Yes. So we would be updating this unit, this column, right? So that we can obtain a new set of values. So that is what we are doing is, so we would be updating W12, we would be updating W22, similarly W23 and W24. So W12, new value is obtained from the old value. What was the old value at this place? 0. 0, 0, 0, 1. The old value was 0, minus of the learning rate, which is 0.2. And x1 is what? 0. This is x1, x2, x3, and x4. So after putting this, we obtained new W12 as 0. Similar case, W22 would be minus of 0.2. And on same case, a similar formula applying this would be W3 to be 0 and W4 to be what? 1.2. So after this iteration, so the new code vector which we obtained. See, this code vector, first code vector would not get affected because it has nothing to do with, because the only change that has been brought is into this code vector 2, because we declared this to be the winner. And we moved this technically away from the input vector, which we were considering, right? So after this iteration, after the training of, or after passing the S2 as input vector, this is the output, right? See, we have not yet completed the epoch. Epoch means we have to consider all the training patterns. See, this is just iteration, first iteration that we have done. So again, we have to move to the next input pattern in this scale, right? So now we would be taking what? The second input pattern, that is S3. Remember, we had input patterns what? Training vectors were what? S2, S3, and S5, right? So now we have taken S3. So S3 is 1100. Now S3 is mapped onto C1 as already given, right? So since this is a supervised version, right? So again, following the same set of steps, step 3, find the distance, which is closure. So dj, again, the equivalent distance. So what we obtained is, with respect to S3, D1 comes out to be 1 and D2 comes out to be 3.88, right? I hope this is same as what we did earlier, right? Now, based on this, definitely the winner would be D1 because it is resulting in a lesser value. 1 is lesser as compared to 3.88. So 3.1, J over here would be declared as 1. Now step 4 covers J is equal to 1, right? Now we have to update the code vectors corresponding to code vector 1, because code vector 1 has been declared as a winner, right? So over here, since the target was also C1 and the winner is also what? C1. So in this case, the first condition would be tested, right? So the first condition gets true, and therefore we would be applying this formula in order to update the first code vector C1, right? W1, right? So we would update the code vectors W11, W12, sorry, W11, W21, W31, and W41. So W11, the old value. So applying the same thing that we did earlier. This was the condition prior to this, right? So after applying this new set of weights, after calculation this would be the condition, right? So new code vector. Again, we have not touched this C2. We have just obtained the new values for only the code vector 1. So this was after applying the second pattern. So let us do see what happens, listed down everything in form of table here. So the initial phase, which I've called as iteration 0, this was the initial C1, C2 was set already. This was the code vector, right? These were code vector, two code vectors that we have taken, right? So when the first input S2 was given, so we compared between D1 and D2, which was winner. We declared C2 to be the winner and the target was C1. So we updated only C2. Similarly, after applying the input pattern 2, right, which was S3, which was declared winner, C1 was declared winner based on the D1 is medium as compared to D2. And the target was also C1. So we updated C1 and after that we obtained this value. So after applying, then again we would have applied what? The third training pattern to complete the epoch. So after applying the third pattern, uh, S4, we would have obtained what? First condition would have been applied because both the things are same. So after applying all the three input patterns, the weight vector that we would obtain is this, right? Now, this is just the first epoch. This has completed what? Just the first epoch, right? So the condition of stopping condition was that we need to reach to a stage where the next weight vector start making no changes into its values. That means we have to reach to a stage where the changes into the vectors almost nullifies or the changes are almost minimal. We can define that percentage of change also in terms of suppose 0.1 error, suppose 1% of error or 5% of error. Anyway, so after applying this algorithm and running this algorithm, it takes around 12 epochs to converge. And after convergence, this is what we have obtained, right? So this is code vector 1 that we have obtained. This is code vector 2 that we have obtained after around 12 epochs, right? Now, this is what we have learned, right? So what we have learned is like code vector 1 we have learned, code vector 2 we have learned, and after applying this, the final LVQ can look like this, right? Corresponding to this code vectors, two code vectors, right? Now, as you all know that we need to test once we complete the training, because this is a supervised learning vector algorithm. So let us take something which we have not considered as the input patterns. Like, so we have not considered this input. So we have taken a new pattern as 1110, which is not there into our previous set of 5 input training sets that we considered, right? So after applying the same code vector C1, sorry, this code vector and code vector 2, we would obtain by the same method, we would see that D1, D2, and we would find that this D1 is the winner. And therefore, we would declare what? It would cluster it into, suppose, C1. So if we're going to look at mathematically also, we would find that, yes, this is new patterns placed in the cluster C1 because this is expected also because it has a greater similarity with the pattern S1, S2, and S3. You can see that. So this is how we apply the LVQ, and it is one of the very popular algorithms, right? Thank you for this session.